Okay, good morning. And you have homework number 1 due today. If you haven't brought it up, you can bring it up and put it in the envelope after class would be fine. Homework is usually due during the class. So when I say it's due on Friday, what I really mean is Friday during class. Okay, and on next week, Monday, we're going to start. We're going to continue on Chapter 2, which will begin today. You'll have homework from Chapter 2 that will be due a week from today. The assignment's up there. So that's what we're going to be doing for the next couple weeks. You do have an exam that's coming up, I think, in about 2 weeks, or maybe a little more. We'll be talking more about that as we get closer to it. Also, today is another one of those days where I have meetings that start fairly early. I will be available right after class, but once I'm done talking with all the students who want to talk with me, I will probably be taking off. So if you need to talk with me, try to talk with me right after class or email me. All right, now, any questions from last class that you had? Okay, then let us begin with Chapter 2 on the exponential function. Now, if there's only one differential equation that you'll know in your entire life, I want it to be this differential equation. dy dt equals some constant times y. So what you're saying is a function is proportional to its derivative. That is the differential equation that will give you the exponential function. Because there is a function that's the same as its derivative, or at least proportional to its derivative. That is the exponential y is e to the bt. E being the base of the natural logarithms, 2.7, 18 to 8, 18 to 8, so on. It's an irrational number, goes on, not repeating. The way to remember it is 2.7, Andrew Jackson, because that's the year Andrew Jackson was elected, which of course we all remember. So if you can remember e to attend to significant figures in that trick. E is kind of the second most famous number in mathematics after pi. So it's a very well-known number, and it's really the only number that will, if you take its derivative, will give you the function itself. In other words, if you just said e to the t and you took the derivative is e to the t. So that's why it shows up so often in these solutions to exponential functions. Here's another property of exponentials that's really important. You take e to the t, and then you take the power n. That's the same as e to the nt. Now, you could just take that as a mathematical fact, or you could use that as really the definition of what we're talking about here. If you take the time and you multiply it by a certain factor, so you say you get 1, 2, 3, you will, it's the same as taking the function and raising it to a certain factor. So if you make t 2 and then you go to 3, that's like squaring or going from the square to the cube. So the fundamental feature of the exponential is it translates uniform steps in time to uniform factors in the function. So let's just draw the exponential here. 0, 5, 10, 15, 20, 0, 1, 2, 3, and I'm going to be plotting e to the t. Alright, so e to the 0. Anything to the 0 is 1. So it starts off not at 0, but at 1. And then it begins to rise. E to the 1 is going to be just e. So that's about 2.7. So it's about halfway, a little more up here. E to the 2 is not going to be twice that. It's going to be e squared. E squared is about 7.4. So by 2, it's going to be up to here, about 3/4 of the way up to 10. And e cubed is about 20. roughly. I mean, these are all approximate. So E3 is going to be all the way up to here. So what you see is the exponential starts rising and then rises faster and faster and faster. Now, oftentimes what we want to have is an approximation for when t is real small. So one approximation, just setting the exponential equal to 1, we can do a little better. You can fit basically a straight line, and you can get a pretty good approximation, and that's really doing the Taylor series for the exponential function. And so it's 1 plus t. So if there's only one Taylor series that you remember, of course there's higher order terms which we can neglect because t is small. So if there's only one Taylor series that you remember this one, because we'll be using this one repeatedly. We're not going to be calculating Taylor series, but it's useful to keep in your little toolkit. Okay, one other thing is sometimes you'll see this equation written slightly differently. Sometimes it'll be dy dt is equal to y over tau. Well, now we can call tau the time constant. The only difference is that tau is 1 over b. B is sort of a rate constant. Tau is a time constant. It's got the same units as t. So generally, if this is time, that's why this is a time constant. So if you can relate the two, let's just like that. All right, so I'll often be asking for the time constant for something or other, and you can really pick it off just like that. All right. Now, some other issues that come up is sometimes doubling time. One thing about the exponential, like we said, steps correspond to different factors, so you can talk about how long it takes to double a function. For instance, it starts at 1, so it's going to then double to 2, somewhere like that, and then it'll double to 4, and these will be constant steps, and then it'll double to 8. So, what we can do is we can try to figure out the doubling time. So, let's first of all write the solution. As you can always put a constant out front. It really gives you the initial condition, because in this case, we're assuming it equals 0, the number is y, but let's assume in general it's y0. E to the, how do I want to write it? T over tau. Now, I want to know how long it takes for that to double. Well, that means if we assume it at t equals 0, it has y0 is the amount. Then for doubling, you want to get up to 2 y0 equals y0 e, and now this would be the doubling time. I'll call it t sub 2 over tau. All right, so the nice thing about this is that these cancel out. And so you have 2 is equal to this exponential. Now, what is the opposite or the inverse of the exponential function? Natural log. You take the natural log, it cancels out the exponential. So I'll take the log of both sides. Natural log of 2 equals the natural log of an exponential, so they cancel each other out. T2 over tau. So in other words, the doubling time is the same as the time constant except for this factor of log 2, which is roughly 0.693. So you can find the doubling time from the time constant. They're just scaled versions of each other. All right. So let's talk a little bit about the homework problems. And in problem 2.3 in your homework. This is the homework that's due a week from today. Let's take a look. Problem 2.3 says what it says. Okay, a child with acute leukemia has approximately 10 to the 12th leukemic cells when the disease is clinically apparent, so when it begins to show symptoms. Okay, if a cell is, I'm going to ask you to estimate the mass, but the one that's most interesting, cure requires killing every single cell. So the doubling time for the cells is about 5 days. If you killed all the cells, you gave them chemotherapy or radiation treatment, killed all the cells except one, how long until this disease becomes clinically apparent? Well, what you'd want to do is you'd say that now you have an initial value of 1. The doubling time is 5 days, so you can figure out what tau is. And then you put in 10 to the 12th for your amount, and you'd solve for the time. And that would tell you then when the disease would become apparent. So in other words, you can, if you give something like chemotherapy, you can put the person or the child into remission. A remission would be you kill off most of the cells and the symptoms go away, but the cancer keeps coming back. Or you could cure it if you killed every single cell. But if you don't get every cell, you get a remission until after a certain amount of time, and then you have to go through the whole procedure again. So this just shows you a little bit of insight on how you can use these functions to solve these homework problems. So that is homework 2.3. Another one is problem 2.5. That's the second one in your homework assignment. In this case, you're growing bacteria in a culture. Growing bacteria in a culture is kind of a famous case where, at least initially, the bacteria tend to grow exponentially. And you can analyze that. And I think it's pretty self-explanatory what they're asking for. They're asking you to find the doubling time. They give you the value of the function at a couple different times. You're supposed to work your way back and find the doubling time through the time constant. So those two homework problems are really just practice using the exponential function. Sometimes we do exponential decay instead of exponential growth. And you could do a decay just by making b negative. But often what we want to do is we want to put the negative sign in and have b be an inherently positive number. So the differential equation for exponential decay would be minus b times y. Now you have exponential decay. Now your solution is y naught e to the minus b t exponentially decaying. And you can also find a relationship between the half-life, that's how long it takes for half of the, whatever you're counting, to decay, say nuclei or cells, and that's going to just be tau times 0.693. It's almost exactly the same calculation as we did before, except instead of here we found the doubling time for a positive function. Here with exponential decay we find the half-life. It's the same type of calculation. And if you look at how the function looks like, it's a function of time when it's decaying. 0, 1, 0, 1, 2, 3, and we're looking at e to the minus t. Again, starts off at 1. By 1, you get e to the minus 1. That's the reciprocal of e. Sometimes when I'm really trying to do stuff quick and dirty, I just think of e as being 3. So it's going to fall down to about a third. If you want to be more accurate, you can take the reciprocal of e, 0.36. It'll be right around here. Then if you want to weight 2, e to the minus 2, that would be this squared, which if I do that becomes about 0.13. And a handy one to remember is if you take e reciprocal and you take the cubes around here, you're about at a value of 1/20th. So in other words, you go 3 time constants out, you've fallen off to about 5% of the original value. So the function goes down like this, never goes to 0, but it gets smaller and smaller and smaller with time. So that is exponential decay. Now, exponentials are so important in biology and medicine that we spend the whole chapter talking about them. You're probably familiar with them already from your math class, but we're going to be seeing them over and over again. So let me ask, are there any general questions about this kind of brief review of the exponential function? Yes?
Yeah, as far as the homework goes, I noticed we're not really given that many problems.
Okay.
To practice, are the exam questions going to be similar to the problems that we are given?
I would say the exam problems are similar. They'll be even more similar to the practice exams, which I will have to you by the end of next week at the latest. Usually an exam will consist of 4 or 5 problems. There might be a few short answer, but most of the exam will look kind of like these homework problems.
Okay.
A little bit longer than just a quick calculation, something that I'll grade, of course, with partial credit. All right. So the practice exam will be the best place to answer those questions. I should have that out. I'll try to get it out early next week, but we will just see how time goes. Okay, so the next thing I want to do is I want to analyze problem 2.28. That's not in your homework, but it's one of the key problems that we're going to be analyzing. So I'm going to erase all this unless there's any more questions about exponentials. Alrighty. So it was interesting when I made the video. I discovered that the video somehow can put on closed captions. And I said once in class that I'm going to erase. I'm erasing the board, and somehow the closed captions misunderstood me and had me saying I'm a racist. So I hope you don't believe that. But anyway, I erased the board. Okay, problem 2.28. Can't totally believe the automatic closed caption thing. Okay, 2.28. When an animal of mass m falls in air, two forces act on it: gravity and the force due to air friction. Assume the friction force is proportional to speed v, and then you got a bunch of things you're supposed to do. First of all, write the differential equation, then solve it, and then there's some additional questions. So, let us do that. Here's your mass, m. All right, there's two forces. You're going to have one, which is its weight. The weight is just m times g, the acceleration of gravity. And you probably all studied that problem in your introductory physics class, where it just falls under the force of gravity. But you also have friction. And if this is falling, the friction would be moving backwards. And we're assuming it's proportional to the speed, kv. That's actually a pretty good approximation if you're, say, falling through a viscous medium like water, small object through water. It's not such a good approximation if you're falling in air with a high Reynolds number. But let's just assume that this is the way that it falls. So we want to find a differential equation. Well, we're going to start with Newton's second law. F equals ma. Okay, so ma, there's the mass, and how do I write the acceleration in terms of the speed? Anybody remember from their introductory physics?
dv dx.
The acceleration is just the derivative of the speed, dv dt in this case. dv dt, acceleration tells you how the speed changes with time. So that's the ma part of F equals ma. And the F part are these two forces. We're going to take down as positive. So you have mg force, and you have a minus kv force. And there you have the differential equation. Oftentimes you want to have the coefficient out in front of the derivative to be just 1. So we can divide through by m. And that will give us just g minus k over m v. This would be the solution to part A. The differential equation deriving the speed. So on an exam, if I had a problem this simple, I might want you to set up the differential equation. Anything much more complicated than this, I would probably give it to you. But you want to be able to understand, really one important skill is being able to translate a physical story into the differential equation. That's one modeling skill that we really want to learn. All right, and another thing that we're going to need to solve this is the initial condition. So I'm going to say we're going to drop something for rest. We're not at time 0. We're not going to throw it down. We're just going to release it. So in other words, v at time 0 is 0, and then it'll start accelerating down. All right, so that is part A. You derive the differential equation. Now we want to solve it. There's got a couple ways. You could, if you've had some differential equations class or advanced calculus, you could probably solve this by moving stuff to each side, integrating. I want to do my favorite method, which is guess and check. So suppose this term wasn't here. Then what do you think you're going to get for a solution to this differential equation? I told you you could get, if you only knew one differential equation and how to solve it. Well, this g's not here, then that's that differential equation. It's got a minus sign out front. So you expect some sort of decaying exponential. So, make our guess. We're going to assume, oh, well, maybe there's some decaying exponential. Maybe there's a constant, an e to the minus t over tau. And also, there could be, in this case, a constant. You sort of expect a constant because you expect something to start falling and eventually reach a terminal speed. And so, as time goes, this term's going to go to 0. You've got to have something to correspond to that terminal speed. I'll write it as another constant. In fact, I want to match my notes. And in my notes, I had this be b. So let me just, so I don't get confused. It's a constant. It can be anything. I put a as my constant out front here. That's going to be our initial guess. And again, this is something you either get from practice and insight, or I give you, or you just try a whole bunch of different stuff on scrap paper until you finally find something that works. I mean, there's a variety of ways you can do it. Okay. Now, before we even start analyzing this and try to figure out what A and B are, I want to do something else. I want to think about this problem. In fact, you can think about this even before you make a guess. One theme in our class is we're going to think before we calculate. So, let us figure out how this is going to behave. V as a function of time. Okay. Initially, your time 0, V is 0. That's our initial condition. And we said that if you have small v's, small values of v, this term is going to be really small. In that case, you just get these two terms. And those two terms is just dropping an object. It's a motion under gravity with a constant force, and you expect the v to increase linearly. So the position increase parabolically. So you expect the solution at small times to be going up like this with a slope that's equal to g, the acceleration. It's the slope of this curve is the acceleration. All right, so we know what happens at t equals 0. We know what happens at small times. What happens at large times? How can we get to that? Well, what would large times correspond to with this differential equation?
A equals G.
Pardon?
Okay, we should have V max.
Yeah, so how would you get it from this differential equation?
From our guess equation.
I think one thing you could do is you could say that when it's been falling for a long time, it's going to reach its terminal velocity, where it's just falling with a constant speed. If it's a constant speed, there's no acceleration. So we can set dv dt equals 0. So at long times, so as t goes to infinity, you expect dv dt to go to 0. It reaches a constant speed. So if you put 0 over here, you just get g minus k over mv is equal to 0. You can immediately solve for v. So the terminal speed, that is the speed at long times, is going to be mg over k, constant. So intuitively we expect this to be mg over k, and at long times it's going to approach that. So we know how the function behaves. The only thing we don't know is how it goes from sort of the small time to large time. But we kind of expect that it's going to behave something like this. Growing with slope g at first, and then turning over and becoming flat with speed mg over k. So whatever, I mean, you don't really know for sure. It might have funny squiggles and things. We have to really solve the problem to find out if there are any. In this case, there aren't, but you can't rule it out. But you kind of know the general shape. So it's useful to actually do that process in your mind so you know what you're looking for before you start solving it analytically. Yes?
I'm not understanding where you got that mg over k.
If you take dv dt and you set dv dt to 0, it's 0 equals j minus k over m v, where this is now the terminal velocity. Then you just solve for v. You bring it over the other side, you multiply by m over k, and you get the terminal speed. All right, so now let's see if we can actually make our guess and see if we can get a solution, an analytical description of this solution. So we have our guess. What do we do next? We stick our guess into the differential equation and we see what it tells us. So the differential equation on this side has dv dt. So we're going to take the derivative of this equation and we're going to stick it on the left side. So what happens if I take the derivative of this expression for v? So I'm still learning names. Lily, I think I know your name. What do you get if you take the time derivative of this? And you get a minus b over tau. The b is out front. The tau comes down from the derivative, e to the minus t over tau. And anything else? Trick question. No. The a, take the derivative as a constant, goes to 0. So that's this side of the differential equation. This side's even easier. I just plug v in here. So I'll get g minus, in the first term, is going to be b times the exponential. So minus k over m b e to the minus t over tau. And the second term still has the minus sign and the k over m times a. Minus k over m a. Now, the thing about this differential equation, it has to be true at all times. So it has to be true at any time. And that really means that these terms that have the exponentials have to match. And these terms that are constant have to match. They have to match individually. Because otherwise, you might make it true at one time, but if it's going to be true at all times, it's got to be true term by term. So, the exponential terms are this one and this one. Let's set those, have to look at those individually. You'll get a minus b over tau, e to the minus t over tau, has to equal minus k over m, b e to the minus t over tau. And the b's cancel, and the exponential itself cancels, and the minus signs cancel, and you end up getting that tau is just the reciprocal of this, m over k. You could almost have guessed that. If you wrote this differential equation as v over m over k, it's going to look just like v over tau. You could almost have just guessed that by looking at the differential equation, that that's going to be your time constant. What else? What else? Well, the constant terms have to be the same. There's no constant term on the left. The constant terms on the right are g and minus k over m a. So we can now solve this for a. A comes over, and you get a equals, and the m comes up top, g over k. So we figured out what tau is, and we figured out what a is just from this process. So we're almost there. We go back to our guess, and now our guess looks like this. V equals b e to the minus t over tau is m over k, plus a, which is plus m g over k. We've made good progress, but we still need b. How do we get b? Anybody have an idea? Nobody has any idea? Yeah.
Did you set v equal to the terminal velocity and kind of just move stuff over to solve for v?
Well, setting v equals to the terminal velocity is just what you get if the time was really long. And that's really already in here. As time goes to infinity, you get e to the huge negative number, which is 0, and v becomes the terminal velocity. So it's a good idea, but we've already kind of got that information. But there's something else that we haven't got. How about our initial condition? We haven't done our initial condition. If t was 0, we get v is equal to b plus mg over k. That's not necessarily 0. So what we got to do is we have to use our initial condition. 0 is b e to the 0, which is 1, plus mg over k. and therefore B is minus mg over k. So now we have B. So we had to use two things. We had to use the differential equation, and we had to use the initial condition. All right, so now our final solution. It's this with this value in for B. So B equals, well, both this term and this term have mg over k, so I'll factor them out. Now I had written this term first, but this has got a positive term, so I'm going to put it first. That's that term, 1, because I factored out the mg over k. Here's B, which has a minus sign. I factored out the mg over k, e to the minus t over m over k. And that is the speed as a function of time and analytical solution for it. So it's essentially looking at this figure, but now we have it in the equations. Now you might say, well, is that unique? Is that the only solution? Or does that just correspond to the particular guess I looked at? Well, if you take a math class in differential equations, they will go through and do a lot of proofs to show that these are unique solutions. If you can get it from a guess and you can match your initial condition and the differential equation, it is the solution. We're not going to do the uniqueness and existence proofs, that kind of thing. I'll save that for the math class. But that's our solution, and we got it. Okay, let's see if it fits, if it works. It's always good, when I say if you're doing this on the exam, it takes 10, 15 minutes to get your differential equation. It's worth spending 1 extra minute checking to make sure it's right. So, first of all, you can just stick it into your differential equation and make sure it works. We won't do that. But let's also check our behavior. At t equals to 0, e to the 0 is 1. You get 1 minus 1, so it really does start at 0. At t equals to infinity, you get e equals minus a huge number, which goes down to 0, and you just get mg over k. That's the asymptotic terminal speed. Let's check one more thing. What happens if you're close to 0 but not exactly? So what happens if this t is a lot less than m over k, so that you have a small exponential? Well, we can do a little bit better than just saying that's approximately 0. What was our approximation for the exponential for small argument?
1 plus t.
1 plus t, or in this case it's 1 minus whatever up here in the exponential. So v is equal to mg over k, 1 minus, and we're going to approximate the exponential as 1 and minus t over m over k. The 1 cancels the 1. That's what it should be, because it starts at 0. Then that minus sign cancels that minus sign. The m over k here cancels that m over k, and this becomes just gt. It's growing linearly with acceleration g. Everything works. The analytical solution is really the same as what you get. So another thing we're going to be trying to do in this class is we're going to try to derive mathematical expressions and then look at limiting cases and special cases and make sure that we understand them intuitively on what's happening. So you want to be able to understand that this and this really mean the same thing. You should be able to look at either one of these and kind of get the key information. All right, so like I said, we're going to be looking at this example over and over in different contexts. Something called Newton's law of cooling is very similar to this when we're looking at the way nerves work, some of the channels open and close in the nerve membrane using equations similar to this. We're going to see it over and over again. So hopefully you want to make sure that you understand that derivation, because it's not going to go away. All right. Now, there's a couple other pieces to the problem anybody have any questions so far on this? Okay, let us look at just a little bit more now. We have, the problem says that suppose you want to compare how different animals fall. All right? So we're going to say that the mass of an animal is basically its density times its volume. So density times its volume is going to be some distance cubed, and maybe there's another constant here. So this might involve like 4/3 pi if this was a sphere, or it's just 1 if the animal was a cube or anything. We're going to assume that all animals are the same general shape, but just different sizes. And it also says in the problem, part C, it says to assume that this constant k depends on surface area. Surface area goes as a squared. And then there could be another constant, I'll call it d. That could just involve 4 pi. It might involve the roughness of the surface, how much friction it presents to the air. But we got these two things. Okay, now, we want to know time constant. The time constant is m over k. The time constant really tells you how fast it's approaching its terminal velocity. So, which of these things is going to, really, in fact, what we really want to do, not so much time constant, we want to look at the terminal velocity. That's what we really should be looking at. Sorry. The terminal speed, how fast it's going once it's reached a steady state. And that was mg over k. Okay, that's mg over k, the terminal speed. Well, mass had rho a cubed times a constant times g, and k had a squared over d. So a cubed and a squared, this becomes just a. So you get basically a bunch of constants, rho c over d and a g, times a is the terminal speed. Now, what does that mean? That means that everything else being constant, we're all made out of water, we all sort of have the same properties, we're all the same shape, but we're just different sizes. That means the bigger you are, the faster you fall. So, if you drop something, say in air, to the extent that this is accurate for air, because it's not exactly accurate, but let's just take it as a model. If you drop a small object, like a little fly, even if it's dead so it's not flapping its wings, it's going to fall pretty slowly because it's really small, so it has a small terminal velocity. Whereas you drop a big animal, like you drop an elephant out of an airplane, okay, it's going to come crashing down really fast. So this then leads to one of my favorite quotes from a guy named J.B.S. Haldane. He wrote this essay on being the right size. All right? And in the essay, he says, first of all, he goes through and analyzing this, not mathematically, but in words. And he says, you can drop a mouse down a 1,000-yard mine shaft, and on arriving at the bottom, he gets a slight shock and walks away. A rat is killed, a man is broken, and a horse splashes. So the faster you go, the bigger the damage is going to be. So if you, for instance, there's a fire and you and your pet cat had to jump out the window, your pet cat's probably going to fall, hit the ground, and not much damage. You probably going to break a leg because you're going to be going much faster when you hit the ground. So it's just an example of how animals of different sizes can behave very differently. We're going to see that much more. That's going to be our main topic for next Monday, is to look at other scaling relationships like this. And we'll go into much more detail on how animal size makes a difference. But today, I just wanted to show you that's one example of where animal size makes a difference. All right, so that is the problem 2.28, and I want to just go over that one in detail. So, let me talk about another one of your homework problems. Problem 2.29. So that's in the homework, that's the fourth one. 2.29 says, okay, let's change the problem. Actually, if you're falling in air, it's a little more accurate to say that the friction goes as kv squared. What difference is that going to make? And then it asks you to do a few things. Well, if you derive the differential equation, you have a v squared instead of a v in your differential equation. And now, that might look like a trivial difference, but your differential equation went from being a linear differential equation to a nonlinear. So they're harder to solve, nonlinear differential equations. Fortunately, the problem doesn't ask you to solve the whole differential equation and find this solution. The problem just asks you to find the terminal velocity. How did we do the terminal velocity here for, in this case? What did we do to find terminal velocity? Anybody remember? Yeah? I've erased it already, sorry.
Going to infinity would eventually lead to terminal velocity.
And that worked for this equation, but if all we had was the differential equation, what did we do?
You said G equal to the kv squared over m.
Yeah, but that's,
Solving for
that worked for this particular example, but I guess what I'm asking is one step back, what did we do?
dv over 0.
We said if it's falling and it reaches its speed, uniform speed, if it's uniform speed, then by definition, dv dt is 0. So if you derive the differential equation, then you set dv dt equals 0, you can just solve for v. And so you're going to have basically mg minus kv squared equal to 0, and you're going to solve for v. So the problem 2.29 is kind of like what we just did in class, but it's a lot easier because I'm only asking for the terminal speed, and you can solve that straight from the differential equation that you derive without having to solve the differential equation analytically. It is possible to solve that analytical equation, or solve that differential equation analytically. It's not too hard, but it's just hard enough that it's beyond what we're going to do in class. All right. Now, I want to spend a little bit of time talking about logarithms and log, and semi-log graph paper, because you'll need that for some of the problems. So I'm going to erase all this, and then we'll talk some more. Alrighty. Now, suppose you have something that obeys an exponential like this. You can take the logarithm of both sides. So let's take the natural log of both sides. So you'll take log of y equals, now what happens if I take the log of the product of a function of two things? What's the rule for log? That means the log of a times b is log a plus log b. Things that get multiplied become added. So if I take the log of all this, I get log of y0 plus the log of this thing. Now, what's the log of the exponential? They cancel each other out. You just get the bt. So by taking log of the exponential, you just get dt. So what you have is log of y is equal to a constant plus b times t. That is a linear function. So if you were to plot log of data instead of the data itself versus time, you expect to get a function not that's rising up exponentially, but is linearly increasing. And that's really what log graph paper does. So let me give you an example. Suppose this is your data. Here's t, here's y. And you get t is 0.5, you get 18. And 1.0, you get 100 and, I'm sorry, old eyes, 137. And at 1.5, it's 1,009. And 2.0 is 7,452. So it's growing very rapidly with time. So some exponential function is taking off. Let's plot it, but let's plot it on what's called semi-log graph paper. So here's your graph paper. And time is just going to look like it always does. 0, 1, 2, 3, it increases in equal increments. But y, I'm going to plot in a different way. I'm going to plot 1, 10, 100, 1,000, 10,000. So this is really, this is kind of like taking the log. It goes up by a constant factor. Yes? Question?
Nothing really. I just, wouldn't that be sort of misleading? Because it's not going by a common factor?
Well, it's misleading in some ways, and it's misleading in that it kind of hides the fact that this is growing exponentially, but it's also very informative in another way. For instance, if you wanted to know what was happening at sort of short, when the function was really small, you would it would all be buried down here almost at 0 if you drew it on a regular y-axis, but on the log axis, you can see the detail. Let me give you an example. Suppose you wanted to look at how the Dow Jones Industrial Average has behaved over the last 100 years. Well, the Dow Jones Industrial Average approximately rises exponentially. There's a lot of noise, but it grows by sort of a constant amount, 5% or whatever year or something like that. So if you plot it on, I'll go over here, if you plot it on just y versus t, it's going to look something like this. And if you want to know what happened back here in the 1930s during the Great Depression, that's a tiny little blip here, where even though it was huge, crashed 50%. But if you plot it on, this would be a log paper, so 100, 1,000. Now you're going to see something that looks like this. It's basically growing on a straight line, but we got the Dow, so it's got some noise. And you see that, gosh, the Great Depression really was a huge change, even though on this scale it was really tiny. So that's what I mean. In some ways, it's deceiving. You miss the whole fact that this is really small, but in some ways, it's informative. It just depends on what you're looking at. So let's look at this data and see if I got this data from an exponential function. So let's see if it really does look like a straight line. Okay, so 0.5, that's here, and it's going to go up to 18. Well, 18 is above 10. Now, 18, you don't go up in constant steps. It's sort of like this, like 20, 50, 100. So 18 is going to be about here, about here. 1, it goes up to 137. That's a little bit above 100. 1.5, it's going to go up to a little over 1,000. And at 2, it's going to be up around 7,000, which is going to be way up here. And that, to a pretty good approximation, if I had drawn it really accurately, is a straight line. So, when you have semi-log graph paper, that's what this is called, semi-log, because one axis is log and one axis is linear. It's essentially, the graph paper takes the log for you by having these funny increments, and you grow up and you go off at a linear scale like that. Okay, so suppose once you find that it really is, and if you want to check and see whether something's growing exponentially, this is the way to do it. You plot it on semi-log paper, and if you get a line that's growing exponentially, if you get some other funny shape, well, it's not exponential. It's growing some way, but not exponentially. Now, suppose I wanted to try to figure out the equation, what y0 and b were. And suppose I convinced myself that this was indeed growing exponentially. How could I find that? Well, if there's a lot of noise in the data, I might want to do some kind of linear least squares fit. And that's a little bit beyond what we're going to be talking about this semester. But if there's not much noise, and in this case there really isn't much noise, I can take 2 points, and I can basically fit and figure out what the slope, what it amounts to the slope of this line. So let's take 2 points. Okay, so back to our original equation. Y is 18 when t is 0.5 equals y0 e to the b times 0.5. And let's also take maybe the the biggest value. Let's take time 2. 7452 is equal to y0 e to the b times 2.0. two equations and two unknowns. Anybody see what would be the best way to go about for solving, for instance, for B? Give you a little bit of a hint. Let's divide these two equations. If we divide these two equations, the y zeros cancel out. So, in fact, I would have rather put in the 7,000 on top. So if we take this equation and divide by that equation, we get 7452 divided by 18, which comes out to be, I didn't write it down here, 7452 divided by 18. So this one over this one, y zeros cancel. You get exponential of b to the 2.0 divided by exponential of b to the 0.5. Now there's another rule of exponentials. If you divide these two, that's the same as subtracting the exponents. E to the b 2.0 minus 0.5. So we're almost there. Then we take the log of both sides. So we get the natural log of 7452 over 18 equals, and the log kills the exponential, and you get b times 2 minus a half. That's 1.5 b. So you take out your calculator, and you take 7452 divided by 18, and that's 414. And then you take the natural log, and make sure you know on your calculator which is natural log and which is regular. You divide by 1.5, and you get b is equal to 4.02. All right, so we now know the rate constant. The reciprocal would be the time constant, or the time constant. Yes?
Couldn't we also just take the natural log of like 18 and then 7,052 and then subtract and divide by 1.5? So
Say that again.
like use the linear equation instead of the original.
Oh, okay, you could. That's almost what we're doing. Because if you took the linear equation, you'd still have two unknowns. So you'd still have to take two of the linear equations. So you just want to take the logs first and then do the algebra. I did the algebra and then take the logs in a sense. You get the same result. All right, so if you want to get y0, you can take any of these data. Let's just take this one. And you can now, we know what b is, so we stick in b, calculate and solve for y0. In this case, y0 comes out to be, I'll skip some steps, 2.4. And so your final function is y is equal to 2.4 e to the 4.02 t. And we were able to get an exponential expression just from the data and the log plot, the semi-log plot. So that's an example how you can analyze data using semi-log paper. Now, again, one of your homework problems is problem 2.10. (2.10) says, okay, so some of these problems are a little long-winded. Following data showing ethanol concentration in blood versus time, and it gives you a bunch of data. And it wants you to plot the data and discuss by what process the alcohol is metabolized. Is that what I'm talking about? 10. Excuse me. Here. Problem 10. Chapter 2. This is a measure of the temperature dependence of the current pulse to excite the squid axon, and then it gives you a bunch of data, temperature, and time constants. Basically, what it's asking you to do is it gives you data for the two variables, and it's asking you to fit the data to a function that looks like this. Time constant tau is a e to the minus b times the temperature. So this data doesn't have to be always a function of time. You can just have a model that says that time constant varies with temperature in this way. And once you have that model and you have the data which is given in the problem, you just analyze it just like what we did here, and you can find what A and B are and your coefficients. So the most confusing thing about problem 2.10 is realizing what the function is that it's asking. It's not real clear whether it wants the exponential to have the tau up here and the t here, or the other way around. But I'm telling you, its tau is equal to A e to the minus b temperature. And you can solve, then analyze, and get an expression from that data. That's that would be problem 2.10. Okay, let me just show you a piece of semi-log graph paper. I'll send you the link, which you can download all the graph paper you want. You can get graph paper with different numbers of decades. This piece I've showed you has 4 decades. This has just 1 decade. Notice that in the linear scale, it's uniform. But in this scale, it goes up from 1 up to 10. And the other thing that's kind of interesting, and it's hard to see probably from where you're sitting, is here's 1, 2. The distance from 1 to 2 is different than the distance from 9 to 10. In fact, the difference from 1 to 2 is the same as the distance from 2 to 4, is the same as the distance from 4 to 8, because they're both doubling. So doubling on semi-log paper corresponds to equal increments. The distance from 1 to 3 is the same as the distance from 3 to 9. Every factors of 3. So if you ever want to divide things up into sort of equal increments on a log scale, usually you'll go like 1, 2, 5, 10. So 1 to 2 is doubling, 2 to 5 is a little more than doubling, but if you just want nice round numbers, it's pretty close. 5 to 10 is doubling. So, or you could, if you didn't want to do that, you could do 1, 3, 10, 30, 100. That's pretty close to a factor of 3. Okay, 3 times 3 is 9, not 10, but it's pretty close. And that's the way like we do our currency. Our currency, we have a $10 bill, a $20 bill, a $50 bill, a $100 bill. We have a $1 bill. We do have $2 bills. Nobody uses them anymore, but they do exist. We have $5 bills. We have 10. So we naturally divide things up in this sort of logarithmic way. So I will send you the link. You can download all the semi-log paper you want. Okay, one more thing we want to talk about with log function. I'll just tell you, it takes a little practice using log paper to kind of know how fast the different values, how the difference from 1 to 2 is, and then 2 to 3 is less, and it takes a little practice to get used to using it. Let's say you now have a function that's not exponential, but it's a power law. X equals a, or y equals a, x to the n. So power laws are pretty common. So you have a model of a system, and you have reason to believe that it behaves a power law like this. Well, let's see what this looks like if you take logs. Log of y equals, well, this is going to be log of a product, so you get log of a plus log of x to the n. Now, what's log of x to the n going to equal? Yes?
N log to the x.
Exactly. N times log of x. So now, if you plot the log of y versus the log of x, you again have a straight line. So this means what you really want to do is you want to have log paper. Paper that varies as 1, 10, 100 on this scale, and 1, 10, 100 on this scale. If you have that sort of paper, you expect a power law to go up as a straight line. So I want to show you an example, and this is going to be example 2.40, which is not in your homework. And we're going to do a sort of an abbreviated version of this. So let me just erase this and let me draw, make a little chart with some data. This is R. This is going to be the radius of a molecule in nanometers. So we're going to be looking at how big different biological molecules are. And not all molecules are spheres. We can give them roughly a radius, kind of a rough size. Versus their M. M is not their mass, but it is their molecular weight, which is like their mass, but it's a dimensionless number. So, water is 16 for oxygen, its molecular weight 16, and hydrogen is each one, so its molecular weight is 18. And its size is about on the order of angstroms. So nanometers would be a tenth of an angstrom, or angstroms a tenth of a nanometer. So a nanometer is about 0.15 for the size of a water radius for a water molecule. It's kind of what we said the other day when we made a box, and we said that the box was like 3 angstroms or 0.3 nanometers. That was more like a diameter than a radius. Okay, glucose. Glucose is about 0.39 and about 180. Glucose is 12 for carbon times 6 carbon atoms plus 16 times oxygen times 6 oxygen atoms and then 12 hydrogen atoms. If you add those up, it should be 180. A molecule called inulin, which we haven't talked about at all, is 1.25, is larger, and about 5,000. And a molecule, hemoglobin, which we mentioned first day of class, which is really big. It's like 3.1. Remember, these macromolecules are on the order of a few nanometers, and it's got a molecular weight of 68,000. What we're going to want to do is, first of all, plot that and see if this obeys a power law. So, you have to kind of be careful here. We're going to have, first of all, R down here in nanometers. This is going to be 0.01, 0.1, 1, 10, 100. And then we're going to do this direction is going to be M. Now, one thing, if you want, the slope of this curve really should be N. If we went back and you looked at that, I said that this would be a linear curve and the slope is N. And if you want to be able to just measure the slope and get N, you have to make sure that the decades on this axis are the same as on this axis. So here we're going to have 1, 10, 100, 1,000, 10,000, 100,000. All right. So let's draw our data. Water is 0.15. 0.1, remember 0.2 would be a third of the way over, so this is about 0.15 here, and you go up to 18. That's above 10, that's about here. Glucose, about 0.39. 0.39, that's a little over halfway over here, and you're going up to 180. You're going up to about there. Inulin, 1.25. That's just above 1, and you're going up to 5,000. 5,000 is going to be way up here. And no, it's not. 5,000, that's 1,000, that's 5,000. And 3.1 is about halfway between 1 and 10, and that's going to be 68,000, so that's going to be way up here. And this is not bad as a straight line. If you really had good graph paper and you did it, you'd write on a straight line. Now, what you could do is, since this is decades the same as that decade, you can just take out your ruler and you can measure the slope, and that would give you N. Or you can do it with the data. Okay, questions on how I made the log plot? All right, so you could just take 18 is equal to some, say that we're going to find M is equal to A, R to the N. That's our model. You can take 18 equals A, R is 0.15 to the N, and you can take another point, which we'll take down here, 68,000 is equal to A, 3.1 to the N. We're running out of time, so I'm not going to solve the whole thing, but again, if you divide the two, the A's will go away, and you'll be able to solve for N. And if you solve for N in this case, you get approximately 2.72. And then you can plug it into one of these equations and get A. You get A is equal to 3140. So you can actually come up with this relationship between molecular weight and radius. It's pretty close to 3. And you'd expect it would be 3 if you were actually, everything had the same density and it just grew molecular weight with a measure of the volume. Then you'd expect it was cubed. It's not quite exactly that. So, let me just show you. This is a piece of log paper. Same website, you can get it. You can go from 1 to 10. You can get different numbers of decades, log on both scales. So you can download all the log paper you want. So we're going to continue talking about Chapter 2 on Monday. We're going to work specifically on scaling, how objects of different sizes behave just because they're bigger. So have a good weekend. If you haven't had it in your homework yet, bring it and give it to me right now.